Recording starts. Okay. First of all, let me introduce our today's guest. This is Bolei Zhou. He's an assistant professor in the computer science department at the University of California, Los Angeles. He earned his PhD from MIT in 2018, and his research interest lies in the intersection of computer vision and machine autonomy, focusing on enabling interpretable and trustworthy human-AI interaction. He has developed a number of widely used interpretation methods such as CAM and network dissection, as well as computer vision benchmark places and ADE20K. He is an associate editor for pattern recognition and has been area chair for CVPR, ECCV, ICCV, and AI. He received MIT Tech Review's Innovators Under 35 in Asia Pacific Award. More about his research at his GitHub site.
Okay, so yeah, thanks for the introduction, Alexander, and thanks for the invitation. So I'm very excited to be here to have this in-person presentation. So I'm looking forward to this kind of in-person presentation for a long time. So as introduced by Alexander, I'm an assistant professor at UCLA. So I joined UCLA early this year. Before that, I was an assistant professor at the Chinese University of Hong Kong. So my research is on computer vision, machine learning, and machine autonomy. So I have done many different kind of research. For my PhD thesis work, I work on the visual scene understanding, like I build the places and also ADE20K for semantic segmentation. And then we have also done a lot of the generative modeling work. And for recent 2 years, my research gradually shifted to this machine autonomy. So try to integrate perception and autonomy together. So today I would like to talk about our research work on this generalizable embodied AI. So I think it's quite relevant to what you guys are doing. Also, we are academia and you guys are industry partners. So I always look for this dialogue and communication or potential collaborations between the two. So I would like to motivate my talk by showing you this video. So I found it very interesting. So it's a video that there is a kit inside the video, and also there is a dog there. So let me play the video first. So from this video, so there are a lot of things going on there. So you can see how this baby actually learns by perceiving and acting. So at the beginning, so you can see the baby is watching this dog biting this paper, and then he seems understand that this paper seems very tasty. Then he or she acts on this observation, and then went there and grasp this paper, and then ran away. Then he trial and error and test by himself, but then he also received this feedback, so the test seems not that pleasant. So from this kind of on perceiving and acting, so this baby actually learned that this paper is not tasty, and he also received the feedback from the environment. Then so you can see we human actually learn from those kind of example, like trial and error, and try to interact with the real world. Then we learn from this perceiving and acting. So in artificial intelligence, so we are also building such autonomous agents. So embodied AI have been very broad applications from autonomous driving also to indoor navigation and terrain navigations. So we are building this kind of embodied AI to perceive the world, and we also try to have this embodied AI to act on the observations in the complex environments. So for this kind of embodied AI, so people usually build this modular pipeline, conventional modular pipeline. So from observation, then we have this perception module try to process the observation. Then there will decision module try to make a decision, what action we should take. Then it will pass into the planning and the control. Then finally, will output the action for this machine or the robots. So from this observation and action, so there is a chain of actions to take. But nowadays, neural network widely used. Then people start thinking about using neural network to replace maybe either the whole pipeline or some of the modules. Then we have this kind of neural decision making. So from the inputs observations, then this neural decision making as a neural network will do all the process, then outputs the action. So besides this kind of neural network as a whole, hide this. Hide it. I don't know where is the cursor. Maybe people don't like this kind of neural network to replace everything. Then people start building this kind of neural modular pipeline. So the basic idea is still same. It's more like we replace some neural network to replace some previous rule-based modules, such as decision modules. Then have this neural network in the loop. Then we have this neural modular pipelines. Then we can train everything still end-to-end. So for this kind of neural network in the decision-making pipeline, so we usually have this kind of setup for this sequential decision-making in the complex environment. Then this kind of interaction between the agent, this embodied AI, and the environment, and then become this sequential decision-making process. Then become a framework of reinforcement learning, right? So this agent, this neural network will receive observation and feedback from the environment, then will take action and input the action to the environment. The environment will proceed. But there are multiple issues here. So one very critical issue for this neural network in decision making is that neural network models we have are very prone to overfitting, so which lead to very poor generalization abilities. For example, we train this agent to interact with the environment, but if we have another unseen environment A, or maybe unseen environment B and unseen environment C, then this agent will have trouble to generalize its skills to the unseen environment. So the very critical issue here is how can we improve the generalization ability of the agents, right? So through this talk, I would like to share with you some of the research work done in my group that try to improve the generalizability of the agent. And so here I summarize the research into three pillars. So these three pillars for generalizable embodied AI. So the first pillar I will see is the data. So for this pipeline, there is the agent and environments and their interaction. So I think one of the most important things is the data, the environment side. How can we improve the diversity of the environment? Then the second pillar I will talk about is on the agent side, is on the representation side. So how can we improve the representation learning and have a generalizable representation? Then the third pillar is a whole pipeline. So because the pipeline is about interaction between agent and environments, then the issue is how can we design a safe and efficient learning pipeline. Okay, so let's get into the three pillars. So the first part is the data side. How can we improve the diversity of the environments? Because we are talking about reinforcement learning, right? So learning in the simulation environments, then we need to take a look at the existing simulation environments. So at least in academia, people commonly use this kind of simulation environments for this decision-making research. People use this Atari environments. Also, people use Mojoko local motion environments to evaluate the learning algorithm. But the issue is we train and test on the same environment. So from a perspective of computer vision researcher, so I'm always surprised by this. So people just train and test the same algorithm on the same environment. How you expect that this agent can be generalized to the unseen environment? So that this intrinsic problem here, like we cannot train and test on the same environments. Also for this simulation environment for driving research, people commonly use the color, right? So it's very commonly used. And also this highway environment is also an driving environment people use. So the trouble for those environments is that their assets and road networks are fixed, right? So for the color, people commonly train and evaluate in the same towns, and all the town maps and also the 3D assets in those environments are fixed, right? So those environments are really hard to use to evaluate the generalization ability of the agents. So we want to change that. So along with my student and collaborators, so we build up this new driving simulator called MetaDrive for generalizable reinforcement learning research. So here I highlight the research because this simulator mean for this research kind of application. So it's still a little bit far away from this industrial level applications. But it's very good tool for prototypes, the different machine autonomy research algorithms. So we already open source this environment there. And one very critical design for this MetaDrive is that we keep a open scenario design. So we can easily generate new scenario and also input new real data in our environment. So those data can be used to replay, then we can use them to train and test this autonomy system. We also design multiple reinforcement learning tasks based on this simulator. So we have the safe exploration, which developed for the safe reinforcement learning. We also have this multi-agent reinforcement learning, and many more benchmark and tasks can be added into the simulation environments. So this simulation environment provides multiple observations. So we have the depth, RGB. We also have this point clouds. We also have this human interface. So later I will talk about some on this human AI interaction work we have done based on this simulation environment. So the key design of this MetaDrive is that we have the procedural generation function inside. So then we can generate an infinite number of driving environments. So here is some configuration files as input to the environment. Then we can generate different road structures. So we can change those configurations, and we can generate a different road traffic assets. So based on this kind of block design, then we also develop some procedure generation algorithm that can generate infinite number of road environments. So here, this demo video showing you this road generation process. So for the generated road structure, we can further turn them into this interactive environment. Then we can train and evaluate the agents inside this environment. So based on this kind of procedure generation, so we can have lot of training and testing environments. So we can then evaluate the generalization ability of this agents for this generated road maps. So we can split them into training and testing. So the plot on the right showing you this generalization performance of the algorithm we trained. So here we just take some baseline PPO baseline algorithm. The horizontal axis showing you the number of training maps. The vertical axis showing you the train performance and test performance. So we have like 50 holdout maps that we can evaluate on those holdouts testing maps. As we have more training maps, then you can see there is a converge of train performance and the test performance, which shows after we have more diverse training data, then the generalization of the agent is greatly improved. Then you can handle this navigation task in this unseen environment. So any questions so far for this part?
So the y-axis is that's like success rate.
Yeah, it's more like a successful rate for
It's
the
like
memory.
reaching goal without glitching.
Yeah, there could be multiple metrics. So right now, this one is more like the accuracy. The accuracy. I think it's about whether you can reach in the goal. But we can have many other metrics. We can also evaluate the trajectories that can be evaluated too.
Okay. What if you, continue like having like hundreds of thousands of training?
I guess this one is more like a log scale. So then we have to have 10,000 environment training. So that will have a lot of overhead. So I guess that relevant, we have to, if we want to keep improving, like maybe 90%, then we have to change the IO algorithm. Right now, the algorithm we use, just some baseline algorithm. Because right now, this plot just try to show the power of the data. The algorithm itself, then we can improve the algorithm, have more sophisticated reinforcement learning algorithm that can potentially improve the performance.
But anyway, it's not just real generalization. It's just generalization in terms of this procedural procedure of generating these maps. Because anyway, we are generating more and more data, but the way of how we generate is the same. So it's not like a real generalization.
Yeah, so later I will talk about we input the real data. You get a good point. Yeah. It's about the complexity of the data. So right now, it's also depending on the data we generated, the data generation algorithm we use. Here is some demo video showing you this agent, training the agent in this holdout environment. So we have 6 this holdout maps. So they have different structures. The agent can handle this navigation task without much trouble. So based on this simulator, we also benchmark many this safe reinforcement learning algorithm. So basically, the safe reinforcement learning algorithm is formulated as a constraint optimization problem. So under this exploration of the agent, we want to make sure the cost is not so large, so then it's modeled as a constraint optimization problem. So we build this safety environment. We also evaluate many different IO algorithm and also safe IO algorithm and also some offline method. So this is the demo video showing you the difference between this constraint SOC agent and the naive PPO agent. So without this safety trainings, this PPO agent will cause a lot of trouble, like running into traffic cones, scratch other cars. Also the cost, then you can see here, we have a cost here. Then there's cost going up. And for the constraint SOC agent, then can keep a cost low and have a safe behavior, exploration behavior for the agent. We also use this simulator to build this multi-agent environment. So that is also very interesting for this multi-agent reinforcement learning community. So here we have 5 this multi-agent traffic simulation environments. We have this roundabout and the bottleneck and the unprotected intersection and tollgates. So in those multi-agent environments, so we have to train a population of agents that they will coordinate with their behaviors to accomplish the goal as a population. So in this case, so each agent will be controlled by one policy. So they have this implicit coordination. So based on this environment, we develop some algorithm called coordinated policy optimization. So here is the bird-eye view of the environment. So we have this target car. Then we build this coordination of this agent with their neighborhoods. Then we build this kind of coordination, 2-level coordination into this multi-agent reinforcement learning algorithm. And then we can have this more coordinated agent. Then we evaluate this algorithm with this explicit coordination with many other multi-agent algorithms. Then we can show this kind of coordination algorithm. have better performance on this environment. We also observe some emergent collective social behaviors. This is interesting because we don't explicitly tell this agent they should do this kind of coordination. They are more like emergent from this coordination reward function. Then they form this kind of a yielding behavior to the other agents, and also there's some competition, this cutting behavior for the vehicle. So get to this point. So besides this procedure generation, we also want to enhance the data loading capabilities. This is why we build this real to scene design, that we can input the real traffic scenarios into the simulation environments. So here I show you two maps. Actually, maps imported from the real data. So the Waymo or Argoverse, they release some data sets, but they mainly release the data for their trajectory prediction. So we just take their trajectory prediction data set and do some modification. Then we can input their traffic scenarios and also trajectories in our environments. So here is a scenario. You can see we try to replicate the real scenarios from the Argoverse data set in the simulation environments. Then after we input this real scenarios, then we can train and evaluate our agents in this real data.
So here, the real data seems to have these buildings, but for you just in the open.
Yeah, so it's very difficult to input the real buildings, because the data set, they provides the HT map and also the trajectories. So there is no building information inside the data set. But potentially we can also have the procedure generation for the buildings. There's some graphics algorithm, and then we can also put some building there.
Yeah, I think it's mainly just the other agent in construction convert the data from real world for each of the vehicles or pedestrians or whatever, along with the map, not the images.
Yeah, just the user bounding box information.
Yeah, we use this already processed information, not a raw image data. I think the image data, they don't provide the full set. They provide some samplings. But we have some ongoing work, try to use some nerve things to reconstruct the things, but that will involve a lot of computations. Potentially, you guys probably are doing similar things. I think that's but there's still a lot of technical challenge to doing this kind of a town level, city level reconstruction. Yeah, it's challenging. But here we just remove this perception part. We assume the perception already done, and we have this kind of top-down view. So we can study this decision making based on this kind of views rather than from the raw data. Yeah.
So using GraphNet or just a top-down rasterization?
Yeah, just a rasterization or some vectorized that we can include. So here are some of the driving. Some of the traffic scenarios inputted from the Waymo datasets. So each vehicles have some trajectories and velocities. So based on the then our simulator can be used to replay those scenarios. To further go beyond that, so we also develop some generative model, try to learn from the scenarios and generate new scenarios. So here is some work on that. So we recently have done that. Try to build some generative model to learn from the traffic scenario. Then we can learn to generate a new traffic scenario. For this scenario data extracted from Waymo dataset, we developed some auto-regressive generative model called the traffic gen. Then we can generate new scenarios. So here is a demo video showing you this generation process, because this is an auto-regressive model. Then this heat map will indicate the most likely vehicle locations. Then we can generate a scenario. So after we generate that, then our model can be further used to generate the future trajectories. Then this generated scenario can be further turned into the simulation environment. So in that case, this simulation environment, this traffic scenario is interactive. It's actually reactive. to the agent, and we can train and evaluate our agent in this generated scenario.
Why do you want to generate scenarios, and also can you control?
Yeah, so because generating the scenario allow us to have this controllability, so we can actually sample from the low probability area, then we can sample more corner cases from that. Also for the, we also can use a generative model to manipulate the existing scenario. Like for this existing scenario, we want to add some new vehicle inside, then we need some model to drive that. Because this generative model can be used to like place new vehicles or generate new scenarios. So that can enrich the diversity of the data we have.
How do you measure the quality of your traffic to gen solution?
Can you say it again?
How do you measure? What is the metric is used to measure that your traffic gen solution is?
Yeah, so that's also an open problem for the generative model, like the image generation. How we evaluate the quality of the image,
especially in the autonomous driving. How to measure it?
So we, because this auto-regressive model is a probabilistic model, so we can hold out a validation set and evaluate the likelihood. So because this likelihood is a metric,
I see.
So how you overfit, how you fit the data. So the likelihood is a metric. We also can use a generative model to run our training agent to see this generated scenario can be used to train our agent. Then we can like run this vehicle and see whether there's some violation of traffic rules. So we also can check the quality of the generated data using this kind of things to see whether the generated vehicles go against violate some traffic rules.
Yeah. So sort of combination of prediction metrics like and like collision and safety metrics.
Yeah, so for the metrics, we can come up with different metrics to evaluate this. But I agree with you, it's an open problem. Like it's an open problem in the machine learning community. Like for the generative model, like generative image, how you evaluate the quality. Yeah.
Thanks. We have a question from Albert, and he's asking, if you're sampling low likelihood scenes to get rare scenes, won't those scenes also be low likelihood in the validation set? How do you ensure the rare scenes are also of high quality?
Yeah, so we can develop this two-step validation. More like we sample, because we can sample basically infinite number of low probability data. Then we have another filters to filter the generated low probability scenes. Like we can proceed, we can have some rule-based criteria and check the vehicles whether they follow the rules. Then we can pick up this corner case, but they also fit this traffic rules. Yeah.
Okay, thanks. And we also have a question from Yuri. Have you considered or looked into using FID style metrics like?
Yeah, FID is also a good metric, but
it's mostly for images.
Yeah, FID is mostly for image, but we can turn this into image and evaluate. This is also a potential way to do this.
Oh, no, I mean, it doesn't have to be images, right? So this is based on embeddings that, for example, some prediction model can produce, and you can compute statistics over that as well.
Mm-hmm.
So like the core idea is, like you look at.
Mm-hmm. Yeah, I think it's possible to develop this FID type of metric to evaluate quality.
And do you like only generate the start position of all the agents, or you also generate like speed or?
Yeah, we generate everything. So this framework. So I think we'll put the paper on archive maybe in 2 weeks. But I can talk about the detail. So this model is a traffic gen is a two-step generation. So we first place the vehicle locations. Then after we place the vehicle, then we turn this into a trajectory prediction task. Trajectory prediction predicts 5 seconds or 7 seconds. Here we extend into predict 20 seconds or predict in this auto-regressive way. After we predict next steps, then we can continue to predict. Then we'll generate long trajectories. So that's kind of we also can have the trajectory of the vehicles for this. So here is the evaluation to see how can we use generate data to improve the real world generalization. So the first row showing you this if we train on real data and evaluate on real data, then we have this algorithm have 60% accuracy. Then if we just use a procedure generated data to train this agent, this agent have very poor performance on this real data test set. I mean, like half of the performance on compared to the model trained on the real data. So we use synthetic data from this generated model, and the synthetic data generated from our this traffic gen. Then we use that as the training data. Then we can have better performance because we can. It's more like we can generate more data, like maybe 10 times more data compared to the real data to do this kind of things. Then we can even improve the performance on the test set a little bit. Also, we can further do some augmentation, like sample more from the low likelihood locations. Then we can preserve the successful rate and further like reduce the safety evaluation on the test set. So that we also evaluate the safety evaluation of the agent, so that can with this kind of augmentation, so we can improve that. So that is showing you this. It's meaningful to learn some generative models to generate more scenarios. Another very interesting application of this generative model is that we can incorporate this generative model into this traffic prediction. Then we are doing some experiment and try to show that can further improve the prediction. It's more like we have this generative model in the loop of this trajectory prediction that can help us to generate better future trajectories. Because more like we can generate longer trajectories for the vehicles.
So you are training a generated model to generate data to train the prediction model.
Yeah, it's also possible. We also can incorporate the generative model directly into the prediction model to help it. So it's more like we have some hybrid models. So yeah.
Have you tried to combine? I mean, so like maybe if you go back to the previous slide and the table. So you show like real data and then like also this synthetic data. Have you like, do they also like combine synthetic data with real data?
Because right now this part is already 10 times larger than the real data. And we add real data inside, then the performance is still very similar. So we hope we can have more data because we just use the Waymo data sets. Waymo data sets are a lot of noisy things after our processing. So we don't get so many scenarios. I think we get thousands of scenarios. But potentially, if we have more real data incorporate, I think that can further improve the performance. You can train on larger data sets, then this kind of samplings can be improved.
And also like maybe like for this data kind of question, if you 10x the data or like 100x, like, normally for computer vision tasks, right? Like you should also, for computer vision or NLP task, you can like make the model larger and then the performance can be better. For RL, have you done any experiments on like playing with it? Because for RL model, it's mostly like MLP. Like a few layers.
Yeah, that's the thing I will talk about in my second part, the representation part. So you raise another very important point about the representation. So I will just run into that. So here is the data part, right? So the first pillar is on the data part, right? So let's move into the second part. The second pillar I will see is the representation, right? So that is underestimated research topic in this reinforcement learning community. Like as we said, the reinforcement learning community, they only use 2 or 3 layers MLP, which doesn't make so much sense, like from perspective of computer vision researcher, right? So in CVPR or this vision conference, you see they design a lot of sophisticated architectures and also design a lot of representation learning algorithm. So I was claim that the second pillar for generalizable embodied AI is the representation learning. So how can we learn a better generalizable representation, right? So So for this kind of learning in the simulation environment, so ideally we want to improve this agent. Then we want to train this agent by interacting with the real world. But that is impossible due to the safety or many other concerns, right? So we cannot like train this policy representations by directly interacting with the real world. But the challenge here, let's say we still want to train our representation with real world data, then what we do, right? So we basically for this part of representation, like how can we like do some pre-training for the policy representation with real world data? Because our lab is an academia lab, so we don't have access to a lot of this driving data with a lot of ground truth. So what we looked into is a YouTube website, because YouTube have ton of data. So we just try to download videos from YouTube. So it happened that some YouTubers actually upload a lot of this driving video to the channel. Like here is a guy called Zhou Utah. So he uploads so many driving videos like, all over the world, from New York, Chicago, and Toronto, and Las Vegas, Tokyo, Morocco, a lot of different cities. Then probably he just flew there and put a camera on the dash cam and drive around. Another surprise me is that there are actually a lot of people watching those videos. You know, there are 8 million views. So I don't understand why this guy uploaded the video, and I also don't understand why there are so many people watching those kind of driving videos. So if you click inside, these are just a very long, like 1 hour or 2 hour driving video around the city. But I guess you get a sense of what the city looks like, then you can decide whether you want to go there. So based on this data source, we just download about 100 of these videos, YouTube driving videos. Now here are some of the video we downloaded. Probably this is a California thing. Then this driving video we downloaded. Then this driving video, you can see the contain a lot of different diversities and also different weather conditions and the urban and suburb scenes, and also this populated scenes, and also this very empty scenes. So a lot of the diversity so could be used as our training data. So we just download all the videos and try to develop some pre-training algorithms. So then we develop, so we have this project that try to learn to drive by watching YouTube videos. So with along with my student Qiang, we develop work that published recently at the ECCV that try to learn the representations from this real world driving videos. So we try to develop some self-supervised learning algorithm on this real world driving videos. So one very common training algorithm or learning algorithm for self-supervised learning is a contrastive learning. So many of you may be familiar with this contrastive learning. So basically, what we can do is we build some contrast learning on the data we have, right? So for some video frame, so we can do some data augmentation, right? Try to crop the image, then we can create this positive pair. Then for the negative pairs, we can use a video frame from another video as a negative pairs. Then we can create this kind of positive pair and a negative pair and train this contrastive learning representation learning method. But the issue with this contrastive learning on the video data frame is that the learning features may not be effective for the decision making, because for this kind of augmentation, the feature may pay more attention to the trees and the skies, which is not so relevant to the driving task, right? So for the driving task, we want to train the policy, right? So we want this representation focus more on this more important area, like this long, this traffic size areas. So then for this kind of pure learning from the image space, so not so effective. Then we try to model the human actions inside this representation learning. So we found out the human action is actually determining the whole driving video. Right? For example, if the human like turning the wheel on the left, then this whole video will become like turning left, then we turning right, then whole video will going right. So this human action is actually the force, the determining force behind this video. So we try to model this human driving behavior in the representation learning. So here is some video we processed, like all the left turning video, all the straight driving scenes, and all the right turning scenes. Then you can see this human driving behavior affects this video a lot. So we try to model the human actions. The issue is that the driving video we downloaded don't have any labels. We don't have any like, human driving behaviors for the data. Then we use some pseudo labeling method based on this.
Sorry, yes, we have a question from Albert. Does this mean you can crawl Google Maps Street View to create driving videos since you don't need any ground truth knowledge about how the video was recorded?
Yeah, basically we can use the Google Street View to train that. But I guess the Google View, they have not like video like continuous. So in our settings, we also want some continuous to that. Yeah, you raise this OpenAI work. So that is actually a concurrent work with us. So even their work is not published. I think they just publicize their work. So I think, so our work already published at the ECCB. So I think the two are relevant, but I will see it's a more like concurrent work. It's more like we also want to learn from the driving videos. So the OpenAI works, they try to, they download a lot of Minecraft video from YouTube, then try to train some agent using this Minecraft data. So they publicize their work more widely because they have a lot of channels to publicize that. But I think they share some similar points. So we use this inverse dynamics predictors. Train on some like Waymo data set, because in Waymo data set they have this driving data. Then we can train some inverse dynamics predictors. So that one is more like giving two video frame. Then we want to predict what action happened between the two. So we use the optic flow of this video frames, because the optic flow have less dependency on the content. So that can better apply to our YouTube videos. So that also addressed the previous Albert's question that because of Google Street View, they don't have this continuous observation, then we can very difficult to extract the object flows. Then we cannot put a tag on the videos on the video frame we crawl out.
We have a question from Brian. Brian.
Hello. I was wondering how did you get the action label? You mentioned pseudo label, but probably I missed that.
Okay, so we train some inverse dynamics predictor on some label data set. So label data set and this Waymo data set, they provide, so they collect a lot of driving data, and they also have this behavior data for the driver's behavior. So then we train this inverse dynamic model. Like this model, after we train, then giving some new video frame, then we can predict what action happened between the two frames. That's why called the inverse predictors. They predict what action happens between the two. So we just use this inverse dynamics predictors to put a tag on all the videos we have.
I see. So if there are labels available for this YouTube video data set, then this part would not be needed, right?
Yeah, exactly. If you guys have this video already have this driving behavior, then you can directly train this kind of representation learnings using so that can give you better performance, because right now this predictor will give very raw prediction. But if you have this ground truth driving behavior, then you can design this kind of pre-training directly.
Makes sense. Thanks.
So after that, now we can put a tag for all the driving videos we collected. Then we can use this pseudo label and along with the diverse video we downloaded to train our representations. So after, so in that case, we design some action condition contrasted learning. So for this writer scenes, for the positive pair, then we can pick up another frame from a video that with writer scenes and create the positive pair. Then for the negative pairs, then we can collect a frame from another like straight drive scenes, also left-hand scenes, that creates the negative pairs. Then we can train this contrast learning method for this kind of pairs. So in that sense, the learning feature can be more independent of the visual features, can be more relevant to the decision making and the actions, because this is how we pull the pairs, and that can learn the features more relevant to this to distinguish different kind of actions.
And I mean, like the turn angle, for example, is a continuous value?
Right now, we categorize that into 3 categories, just left, straight, and right. Potentially, we can have more the fine-grained categories. So I think that can potentially improve the performance of the features. Right now, because we are using this pseudo label method, so it's not that accurate. So we just categorize into three classes. But potentially, you can have more fine-grained or maybe continuous value to train that.
How about speed?
Yes, speed we just ignore here. The speed is relatively difficult to predict for this.
But if you have like optical flow, right? Like, I mean, and
yeah, so that speed I get, but it's still like optical flow is on the like 2D image plane, but for the speed is more like 3-dimensional metric, so it's a little bit hard to predict. But for the
maybe visual.
Yeah, Brian.
Sorry. I was just wondering, maybe some sort of visual odometry estimation could give some rough.
Yeah, potentially we
feedback.
can incorporate some geometric priors here that can further improve the performance. It's actually, I'm talking to my student. I try to incorporate some geometric constraints or priors that can potentially further improve the performance, especially if you already have some ground truth like this driving data and also this ground truth or maybe LiDAR data to help this kind of representation learning that can further improve the feature. We'll see.
So when you say action conditioned here, the model itself is not necessarily conditioned on the action itself. It's rather the positive and negative mining is conditioned on the action, right?
The contrast learning condition on the action, right? It's depending on how we extract the pairs, because the pair really is about the action. We use the action to generate the pair, then the contrast learning will rely on the pairs we generate.
Okay.
Yeah.
So what is the eval metrics you use for that?
Or evaluation?
Yeah, how do you?
Yeah, this one I will talk about.
Okay.
Yeah, so this figure is showing you how we evaluate the features. So we then, after we learn the representation, so we just plug in the color simulations, because it's more realistic compared to the previous MetaDrive. Then we can evaluate their features. So we evaluate this pre-trained representation for imitation learning on the color. So this table is showing you that we have a different number of demonstration sites, like 10%, 20%, 40%, 100% of the demonstration data. So under different demonstration training data, then we use the data to train the last layer for all the representation we have. Then we compare with some like MoCo with some supervised learning method, also ImageNet with some training representation. We show that the train from our method can perform better on the previous representations under different data domain. If you only have 10%, that can have greatly improvements over the previous methods. After we include 100% demonstrations and the margin slope, but we still outperform the previous weights. Also, more noticeably, this ARCO representation can perform better than ImageNet, because ImageNet, they train to classify dog and cats. So it shouldn't be useful for this driving task. Right? So this is, of course, our representation should outperform the supervised trained on this ImageNet.
Is this task, do you have route or goal for as conditions for this task?
For this imitation learning, I think it just try to imitate. So I'm not so sure about the settings, but I think they just provide a lot of trajectories into.
So it doesn't really matter, for example, at crossing, like doesn't matter which way you go.
Mm-hmm. Yes, it doesn't really matter. I think it's the color, they have this defined task. So we just take their predefined task and also their data to train that. So if you want to know more detail about their imitation learning setup, so you can go to check their settings. So we just reuse their settings and also keep all the pre-trained model the same, how we use, then evaluate that. So that then we can have this apple-to-apple comparison for the weight.
Makes sense.
Also, the Kara provides some reinforcement learning. So we also evaluate the reinforcement learning performance for this pre-trained weights. So on the left is this reinforcement learning demos. So it's not that ideal because for their settings, they don't have any human data. So the agent will learn this weird like drunk driving behavior, but they still can reach the destination. That's their setting. So we just evaluate how well our pre-trained weight can improve the sample efficiency. The horizontal axis showing you the number of samples. The vertical axis showing you this navigation task for this reinforcement learning. And you can see this blue curve showing you this pre-trained weight can outperform the previous like supervised trained ImageNet weight and also some local representation weight. That shows the power of the representation. So I think later we have more method to do. So Albert asked about what is y-axis. Y-axis is the performance for this reinforcement learning agents. I think it's about the percentage to reach the destination, reach the goal for this. So mostly it not work so well because usually for the Kana imitation or Kana reinforcement learning task, they don't input the first view observation. The inputs, they usually evaluate on the top-down view. Because you can see for this train from random, so there is no performance. So they just give up to use the first view as an observation. So we just use this task to evaluate how well this representation learning can help on this task. So we just show that you train on this, pre-train the representation on the driving data, then that you can use the first view observations for this reinforcement learning tasks for Kali. Okay, any questions for this part?
So I mean, like your previous one, the data one is more like on the top-down view, and then vectorized representation. Right? But then your second one is on the image.
Yeah.
And do you also like
combine the
representation for like top-down view?
Yeah, so that is relevant to the visual appearance of driving simulator. So right now the driving simulator, we don't have very realistic first view observation. So that's why we use a top-down view to study this decision makings. Also, it's relevant to that if you directly train this reinforcement learning agent on first view observation, so it's not gonna work. So this is why we have this second part of work, try to improve the representation. So after we improve, have a very nice representations, then we can train further reinforcement learning using this pre-trained weight. People show that if you directly learn this kind of very so here, this representation we use is a ResNet 50. So if you use ResNet 50 from scratch for some reinforcement learning algorithm, it's not working because about the representation learning problem. And the supervision you get from the reinforcement learning reward function is too weak to train your representation. So there should be some pre-training steps. So this is why we come up with this policy on pre-training designs.
Yeah, I guess ResNet 50 probably explains why the random initialization is not great.
Yeah, it's not great for this. Yeah. Okay, so then let's move into the third part. So it's about the running out of time. There's some time limit.
No.
Okay. So the third part is about learning pipeline. So how can we design a safe and efficient learning pipeline for the interaction between agent and environment. So as I showed you previously, that's this naive reinforcement learning pipeline, the interaction, the trial and error exploration of the agents. So you will end up some agent like this, just doing this crazy stuff, right, through this trial and error exploration process. So that is not so good for if you want this real world application. So no safety guarantees for this kind of reinforcement learning framework. So we want to improve that. So how can we have some safety guarantees for this? That's why we develop another framework that we call human in the loop reinforcement learning. So we want to put human in the interaction between agents and environments. So in this case, you can think about the human as some guardian, right? So it's more like parents to look at our children. If the children just play well, don't run into some trouble, so you just let them play, right? So then there are two roles for the humans. So the human will safeguard the active exploration of the nerves. So at the same time, you also want to have allow the children to have some freedom to explore the environment, because they can learn faster by interacting with the environment by their own. Also, at the second role is that at this when needed, this is a very key word. When needed means when the children run into dangerous or risky situations, so the parents should stand out and help the children and demonstrate the correct action. So we try to model the two roles in this learning pipeline. Then we develop this guardian learning framework. So in that case, the guardian will monitor the exploration of the learner, and then he or she will intervene and demonstrate the correct action when needed. So we can between the interaction between agent and environment, we have this guardian mechanism inside. So there will be a human expert or some pre-trained policy experts there to help this agent. So one technical challenge here is that because there is this involvement of guardian, then the data we collect become more like a mixture trajectories. More like the previous parts of the trajectory could be done by the learners. Then the learner run into some trouble, right? Then there are some intervention. So start here, then the expert will take over the control. Then the later part of the trajectory will be generated from the expert demonstration. So in that case, the trajectory, the training data we collected become mixed. So if you have some knowledge on reinforcement learning, then in that setting, then it become like off-policy learning. So for this off-policy learning, it's still a long-standing problem. Like how can you learn from this kind of mixed data? So to address this issue, so we developed some method called the Human AI Copilot Optimization, shortly for HACO. So it's a reward-free learning with intervention minimization. So in this case, so we don't need access to the environmental rewards. So we design this pipeline to minimize the intervention from humans. So there are some technical design here. So first, we have this Q function. It's a proxical Q function that we want to learn from the partial demonstration. So here, for this Q function, we use some technique from offline reinforcement learning, so called the conservative Q learning. So for this, to learn this Q function, so we train this agent to minimize the two terms. The first term is try to train this agent to be pessimistic about the agent's own action. And the second term is using the same Q function, but the expert action inside. Then we train this agent to be optimistic about the expert action. So it's a little bit similar to this kind of contrast learning, but we have this kind of optimization. Now we can better incorporate the behavioral demonstration from the experts. We also incorporate another intervention called Q function to minimize the human intervention, because we want this learning agent can become more and more independent, cannot exploit on the agent, on the expert too much. So we want to minimize their asking for help, right? So then we want to also minimize this intervention on cost queue function. So in that sense, then we can have this policy optimization, try to maximize the previous proximal queue function, and also try to minimize the intervention cost function in this case. So after this kind of trainings, then we can better efficiently use the demonstration from human. So here is the demo video showing you how this learning, this hardcore method work. So here is a real training video. So we don't cut this video. It's just the training process from the beginning. So you can see at the beginning, there are a lot of demonstrations. So here I'm showing you this training time. So the human experts, basically my student, will play this video game, and we'll do the demonstration to the agent. So we'll learn together with this agent. So at the beginning, there are a lot of interventions, a lot of demonstration to the agent. Here we just speed up. Yeah, so after like 20 minutes of training and this copilot optimization, then this agent already learn how to drive in this MetaDrive environment. So here there's no intervention involved, so this agent can accomplish this kind of driving task and can learn from this demonstration of the human. Here's another demo video showing you this learning process in the color environment. So here is an uncutted video with a training time. So there will be a warm-up step, like human just to do this positive behavior cloning. Then gradually this agent will pick up some driving behavior from the human. After like 5 minutes of training, then this agent already learn how to drive in the straight road. And you notice there is a corner coming. Then this agent don't know how to handle that. Then there will be some intervention from human to do the demonstration how to turn over the vehicle. So yeah, after like 10 minutes of kind of demonstrations, then this agent already know how to drive in this color towns without intervention from the human. So that demo showing you that this kind of human in the loop learning is actually not that expensive, right? So after like 10 minutes or 20 minutes of demonstration, then this agent will pick up the demonstration from humans. Also, we can better utilize the intervention from the drivers, the expert. Like Tesla have this autopilot function, right? So sometimes there's some problem happen, then they will ask the human driver to take over. Then they can collect this kind of information to optimize their system. So this kind of intervention is also very important because a human can decide which is a corner case for the agent to learn. So that would more like give some labels to the agent. So the agent then can focus on to improve this corner case, then can solve this kind of navigation task.
I have a question.
Yeah.
So when you say like it learned how to drive from like 20 minutes, does the driving technique generalize to other domains? Like if you change the driving scene, can it still drive?
That's depending on the. I think in our paper we evaluate the generalization ability, so it can be generalized.
I see.
But it potentially should be combined with the representation learning part. So right now for this Carla, we use a top-down view, like bird-eye view representations. Because usually it's a learn faster use a bird-eye view as an input. You will want use a first view observation, then we can combine with the second part of the work. So it's still ongoing. Yeah.
I see. So let's say if you are using the top-down view and you can, for example, you can already see all the lane markings. So like, what is the challenge here for like the agents?
Yeah, the agent is how to learn the driving behavior from human.
So like the low-level controls.
Yeah, no level control about the vehicles. Because at the beginning, this agent have no idea what this traffic size, this lane size is about. So it's more like we try to help the agent to pick up the important things. It's more like a learning from demonstration or this imitation learning. This work is belong to imitation learning, but different to imitation learning. The difference is that we want this agent have some active exploration of the environment.
Do you think it could generalize to like human demonstration of some emergency or like some harder cases? For example, like because in applications like following the links is not too hard, or maybe you don't need the RL agent, but maybe, for example, if you have an emergency where a person try to circle your car and you don't know what to do, and maybe human can demo, and then maybe the agents can. So do you think it can generalize to like more difficult events?
Yeah, that's our best hope. This is also the future work of this live work. So potentially we want to extend to the broader case. So right now we just demonstrate that this kind of active human intervention can help this agent to learn faster and more efficiently. But for these harder cases, so we don't evaluate that yet. But I think there are some potentials here. It's more like human demonstration for this harder case, more like you put a label for the agent, then we can focus more on that.
Also the question is, for this very easy case, in fact, we have here 20 minutes of learning, active learning. But suppose that's really crowded intersections, multiple agents on the road and so on. How much time would it be needed to learn by simulation here?
Yeah, so I think that will involve the observation. So if you can detect the observation and turn it into bird's eye view, then can be better handled in these cases. But if you want this agent to also build a representation to detect the pedestrians and all the vehicles, then it will be very challenging. That's why here we use bird's eye view as a representation to do this. So that will make an assumption that the perception already solved, but it's far from solved. Right? So we can have better perception, and that can just input this more like a structured representation that can make the later decision-making learning faster. That's what I'm trying to see. This is why I put our work into 3 panels, try to split into several parts and to tackle. If you want a whole pipeline to solve everything, then it's impossible.
I'm just a little bit curious that this active learning seems that we can really fast learn by using human demonstration. It's just sort of Pareto principle here. We can learn like very fast on very simple cases, but when we need to go one level above, we need much more work to be done. And work, sort of.
Yeah, potentially could be the case. Yeah.
So what is?
I'm curious. Sorry, wait, go ahead.
So I mean, like this looks very similar to imitation learning, right? As you said, and maybe like you also have like the dagger issue, and that's why you can get this intervention.
Yeah. So
I mean, but you formulate this one as like RL. What is the advantage or like the difference? You mentioned maybe here you can allow.
Yeah, so I can list several differences. So the first difference, imitation learning is imitation learning have its own trouble, like behavior cloning. So one issue is the expert data is very far away from the learner's data. So there is a clear like distribution shift. It's also a common problem for imitation, like behavior cloning. There is the covariant shift issue, which means the expert data is very far away from this learner's data. So for our case, these 2 sets of data are actually directly linked. That's why we have this mixed trajectory, right? Mixed trajectory. So part of the trajectory are the learner's data, another part of the trajectory are the expert data. So in that case, it's actually easy the boundaries between the learner's domain and the expert domain. That actually we will see it improve the efficiency of the learning. It actually addresses the covariant shift issue for behavior cloning.
Yeah, but say for example, like if I were developing some imitation learning, I might have some driving data, and I can try to first learn some initial policy, and then maybe can have this policy to drive on loads, and so that in cases where the policy drive well, and human doesn't do anything. If the policy starts to do something stupid, and then you take over, right? Would that be very similar to?
Yeah. This is actually the setup for us. So at the beginning, like first 1 minute, so we are doing this passive behavior cloning imitation learning. So that one, so each step, this expert have to imitate the learner have to imitate the expert behavior for the first like 1 or 2 minutes. So after that, then this learner pick up some driving behavior, then it have a higher degree of freedom to explore. Then as long as it doesn't run into trouble, then it can do it itself. But if run into trouble, then human will correct its behavior. It's more like a more active learning, more like human more active monitor this process. So the data generated through that way is much better than this passive driving. You can also like drive in the car or human control everything. Then I will call it more like passive data. So this passive data, the training value for this passive data is very low compared to this active learning data.
Yeah, I mean, like the Dagger kind of thing is trying to address that, right? And Dagger is more, it seems to get it.
It's a little bit similar, but here we also have this agent have the potential to outperform the expert. Like Dagger is more like the upper bound will be the human performance. Here we also want to have the potential this agent can go beyond the expert. It's more like the AlphaGo, AlphaDeo. We want to have this superhuman performance.
But do you have like some number or metrics to demonstrate that?
Yeah, we don't have number for that part. I think that is a like superhuman agent will be more futuristic. Yeah. Okay, so last part. So I would like to briefly talk about this human-in-the-loop inference. So for the first work, so this human-in-the-loop learning is in the training, right? So after the training, so then this agent will just do things by them own, like accomplish this task. But have you thought about this kind of human in the loop inference? Is more like in the testing time, human collaborates with AI to accomplish some tasks. This kind of human loop inference is actually widely existing in the real world, particularly in this kind of human machine teaming, and also this kind of shared control, like the human collaborate with robots to accomplish some task. Also for this kind of skeleton applications, like think about the Ironman, right? So you have this skeleton, so there are some wearable robots, wearable AI that control the system, and can cooperate with human to accomplish the task. Like a human then can lift heavier, can jump higher, right? This kind of a hybrid system is also a direction I'm pretty excited about. This kind of human machine teaming is also a future direction, right? So we have some very recent work that try to do this kind of human AI shared control. Also, it's relevant to the interpretability of this IO agent, right? So for the previous IO task, if you just train this agent to do this primary task, like just to move forwards, this stupid agent can only do this task, right? Very boring task, just move forward. But how about we want to control this training agent? Like we want this agent like stop there, maybe do some trick, like stop there, spinning around or turn left or right, right? So there is no control for this agent. It's also relevant to the interpretability of the agent, right? So it's actually relevant to my research research direction. So one of the research direction in my group is about this AI interpretability. So how can we understand this internal representations? What have been learned inside? Like, then we develop some method called policy dissection that try to open up the black box of the agent and through some frequency analysis work. So basically what we are doing is that we collect a lot of observation for this trained agent. After we collect trajectories, then we can measure different kinematic attributes of the agent, like the velocity, Vx, Vy, and the yaw rate and heating. Then we can correlate this kinematic attribute with neural activations using some time series analysis method. Then we can label the internal representations. So here we just label this internal unit, like internal filters. Then this internal representation then will correspond to different behavior. So then what we can do is that we can activate and deactivate certain internal activations. Then we can evoke some behavior of the agent. Like we can decelerate the agent, and we can make this agent spinning around and heating up. So that is leading to very cool application of this human AI shared control. Here is a demo video. And after we apply this probability deception to this pre-trained representations, then we can associate their label unit with some keyboard key. Then user can press a certain key. Then we can activate certain behaviors from the agent, like this agent. We want this agent move left, then press a key.
So like a semantic dropout.
It's like semantic dropout, also semantic activation. We also want to activate certain units.
Okay. Mm-hmm.
Yeah, we want this agent to do this spinning around, dance around. Then we can press a key. Let's just stop there. Then this agent will stop there. Then we can turn this autonomous agent into more controllable agent. So here's another environment we are testing. So this is a lagged robot, right? So at the beginning, this agent cannot achieve this task. Then we apply some reinforcement learning agent algorithm. Then the agent can achieve this like moving forward tasks. But if we directly deploy this agent in the testing environment that full of obstacles, then this agent cannot handle it. This test environment are quite different to the training environment. Then we have this hybrid human AI control, human AI shared control. Then the agent can just press some key. Now it's more like giving some high-level commands and order to the agent. Then we can control this agent in the environment. It's more like a gamify this environment and have this controller. Then move left, let's stop there, move right, then we can press a key, move forward, then the agent can move forward. Then you can follow the order of the human and to accomplish this task. Through the whole process, there is no like training or retraining for the agent. So we just reuse the learned representations to accomplish this task. So here we then evaluate some performance. So here we call it test time generalization. So test time generalization means in testing time, we don't want to like retrain the model. So we still want this agent to generalize to new environments. So here's some evaluation. So we directly train this environment, then have very high performers, like 400 scores. Then we put this training agent in the test environment, then the performance drop a lot because the two environments are quite different. There is a domain gap because this test environment has a lot of obstacles the agent not trained for. Then if you can have this kind of agent and the human shared control, then we can boost the performance, although we just reduce their previous pre-trained representations, right? So we can, and then we can compare to this agent just train in this testing environment, then we can get a comparable performance for this. So this type of human AI shared controls can greatly improve the generalization of the agent. So here's another, we evaluate on some new environment in the ESOC gene. So that is the environment is developed by NVIDIA. So we use the environment to train on this bipedal robot. It's called Cassie. So this robot Cassie, it have two legs, just trained to move forward. So after we have this agent, then we apply this policy deception to discover different skills from this agent. You can see that Cassie can have this even backflip skills. They can discover a lot of these hidden skills for this agent without pre-training. Now here we can apply the skills in the new testing environment. So here is a shared control. At the beginning, this agent can only like move forward. Then we can ask the user to press a key. Then this AI will implement this low-level control for the agent, like jump over the barrier. Also the crunch, passing this bar. Yeah, to accomplish this parkour, very challenging parkour environment. So this kind of human AI shared control, I think, will be very important to future this human-machine teamings, like how human can maneuver this more complex robot.
So for this dissection, it's all like predefined kind of actions that you are trying to discover, right? As opposed to learning some clustering of.
Yeah, it's more like a unsupervised discovery. So when we apply our policy dissection method, then we can identify this internal representation correspond to some kinematic attribute. Like the backflip is more like a jump higher, then have some yaw change. Then it's more like we activate this agent to jump, but then activate another region for this like a Y velocity, and can turn over. And when they land on the ground, then can adjust itself.
I'm still confused. So how do you like discover like meaningful actions out of like just a random combination of like activations?
Yeah, for turning left and turning right is easy to understand, right? For turning right and turning left, so it's just relevant to the Y velocity or X velocity. So we just try to identify the certain representation relevant to the Y velocity or X velocity.
So,
right?
How do you identify? Do you like just write the heuristics to say, okay?
Yeah, we just record all the trajectories. So after we train this agent, then we just do a lot of rollout. So rollout will generate a lot of trajectories. Then we collect trajectory. We also collect the internal activation. Then we do some time series analysis to see which activation correlated or relevant to the certain kinematic attribute.
So just try a lot of things and try to find semantic meaningful actions.
Yes, internal representations.
So just curious, like, did you find any like interesting behaviors? Like
backflip.
yeah, like I don't know.
Yeah, those are the skills.
skills.
Yeah, those are the skills we discovered. Like the 6 skills are all discovered. Original primary task is just to train this agent moving forward. Those are more like emergent skills inside the internal representation that discovered by our method.
Doesn't it mean though that the agent that you trained to move forward was just suboptimal? Because if it was perfectly optimal, I would not expect it to produce any trajectory that would go to the left or right or do a backflip.
Yeah, I would say that could be like multiple solutions to accomplish this moving forward task.
Yeah,
So that just more degree of freedom.
We have a basis of different actions, and this is just a projection of these different actions into one direction.
Yeah, I mean, I guess I would, if the reward function to go forward was fully maximized, I would think that there would be very, like backflip should not be one that should be
sort of mostly pre-trained like model, not just fully trained. Yeah, I have a question, very tied together with the questions of my colleagues. Don't you think this policy dissect is very similar to lottery ticket hypothesis? When we at any maybe random initialized neural net, we can find the path leading to a solution that we need, for example, for classification. If we are talking about, for example, images for array, maybe the same. It seems like a very tight idea connected.
Yeah, so that's relevant to this recent trend, this random weight network, or this weight agnostic network. So it's relevant to that. So it's touching this more fundamental problem where the knowledge is. So knowledge could be the trained weight or could be the connection along the things. If you just change the connections, then that also can give you some knowledge. So that will, I guess, will lead to more broader discussion about what knowledge inside encoded, how knowledge encoded inside the representations. It's also relevant to the task complexity. I think if the task is very complex, then this agent have to develop a lot of the sub actions to accomplish that. That can also have more better, wider, more number of this emergent behaviors. If you can have this primary training task, is very complex, and you use reinforcement learning to accomplish this task, then the agent like itself will develop some like hidden or implicit sub action that can be discovered by our method. Okay, so to summarize, so I talk about 3 pillars about improving the generalization ability of this embodied AI. So from the data, to the representation, and finally to the learning pipeline. So thank you guys for your attention. So here I list all these works. So they're all open source, and so you are welcome to check it out. And also I am building a new lab at the UCLA, so you are welcome to visit, and also looking forward to some potential collaborations in the future. Thank you.
Yes. Thank you very much for a bright talk. Let's finish.
Thank you.